So, hi everyone. My name is Hao, and I'm currently a postdoc researcher at the UC Berkeley Skylab working with Jan Stoica. And welcome to the RE Summit 2022, and welcome to my talk. And in this talk, I'm going to tell you about a very, very new system that we built at UC Berkeley, on top of Ray, of course, called Alpa, that can automate the model parallel training and serving of large neural networks like GPT-3. And the project is a collaboration between UC Berkeley, Anyscale, and many other institutes. And before I dive into the detail, I want to first share two links. So the first link, alpa.ai, is our project page. And the second link, opt.alpa.ai, is a free online service that you might be interested in. So it provides a free, unlimited GPT-3-like text generation service powered by Alpa and Ray. And as far as we know, this is the first free GPT-3 text generation service in public, because if you use OpenAI service, they will charge for each token generated. And please visit this link and give it a try, and I guarantee you will find some interesting results. Okay. And let us begin with some background on large models. So probably as every of us here already know, a lot of recent advances in deep learning are enabled by large models. And since 2018, the largest model size started to increase more than 10 times every year. And 2 years ago, OpenAI released the famous gigantic GPT-3 model with 175 billion parameters. And this model is recognized as one of the most important machine learning breakthroughs. And today, the benefit of scaling model size does not diminish. And people are still trying to train larger and larger models. And meanwhile, large models are also made more and more accessible to the general public. So 3 months ago, Meta open-sourced a pre-trained language model called OPT with 175 billion parameters and making large language models at this size publicly available for the first time. And about a month ago, the Big Science Initiative open-sourced another language model called Bloom with 176 billion parameters, and another large language model in open source. So as a machine learning developer, how can we embrace large models? While large models can provide a lot of benefits, it also poses a lot of challenges in computing and systems. So to see the core challenge, let me use a simple example. So many of today's machine learning programs often assume the model, such as this BERT, can fit into the memory of a single device, like a GPU. And with this assumption, all the computation is conducted on a single device using frameworks like TensorFlow and PyTorch without any problem. However, when the model becomes large, it's hard to fit the model or even a single layer of this model into its limited device memory. So how can we train and service big models, right? And the only possible way is to partition and parallelize these big models on more devices. However, these steps requires a big amount of engineering effort that is specific to both the model definition and the cluster. That comes Alpa. And Alpa is a system we designed on top of Ray to specifically facilitate the training and serving of such big models. And hopefully after this talk, you could be convinced that Alpa can help you better embrace these big models in your research and development. So to introduce Alpa, let me begin with the computational pattern of deep learning. And first, we have a batch of input images. And we feed input into a deep learning model. And the computation involves a forward propagation to compute the predictions, and then a backward propagation to compute the gradients and update the model. And now if we want to scale this training pattern, we face two problems. So first, what if the input data is very large? For example, we want to train on millions of images. And second, what if the model or the model layers are very large? For example, we want to train a model with billions of parameters. So the difficulty of these two problems are quite different. So the first problem is easy and has been studied pretty well. It is called data parallelism. And we can partition the input data and replicate the model. So here are 2 GPUs, and we can replicate the model on 2 GPUs, and then feed different input batches to different GPUs to parallelize this computation. If you are a current Ray user, this pattern is actually addressed pretty well by the new Ray AI runtime, where you can find a ton of interfaces in Ray to parallelize this pattern. But the second problem is much harder. If the model is very large, the size of the model can be much larger than the device memory capacity. And as shown in this figure, we need at least dozens of GPUs to hold this model. So we cannot afford to replicate the model. Needless to say that we have to store a lot of intermediate results. So we also have to partition the model. So however, Unlike the dataset, which are just a sequence of images or sentences, the model is a complicated computational graph, and how to partition this model is non-trivial. So now let's take a look at the computational graph and explain why it is so difficult. So the graph begins with an input x, and we then have a lot of matrix multiplications, convolutions, element-wise activations, and reductions, etc. And the figure only shows the forward propagation of the graph. But the real graph will be more complicated with the backward propagation and the gradient updates. So how can we partition the graph onto two devices here, device 1 and device 2? So the most straightforward way is to cut the graph in the middle and put them on two devices. This is called intra-operator parallelism. And the cut is actually not too bad, because the communication between the cut is actually quite small. However, due to the data dependency, the second device cannot always be busy. It has to wait for the first device to generate its input. So the second device will be idle at some time. And although this can be elevated by using pipelining, it still results in device idle time due to the dependency between forward and backward propagation. Now, if we want all devices to be always busy, what should we do? So instead of partitioning at the graph level, we can partition each operator and let different devices work on different regions of the same operator, as this figure shows. And this is called intra-operator parallelism. And intra-operator parallelism makes all devices busy, but it leads to more frequent communication because devices have to think after one operator if the next operator cannot preserve the previous partitioning pattern. So in summary, this page shows two basic patterns of partitioning a graph, which is also model parallelism. As I just mentioned, there are trade-offs between these two methods. So intra-operator parallelism requires less communication, but has more device idle time. But intra-operator parallelism requires more communication, but less device idle time. So under this classification, there are more variants. So first, for intra-operator parallelism, there are multiple possible strategies to partition an operator. For example, for a matrix, we can partition along rows. We can also partition along columns, or we can even replicate it. And when connecting this node in a graph, different partitioning strategies can lead to different communication and computational costs. And this is a very difficult combinatorial problem. And for intra-operator parallelism, we can increase device utilization by pipelining the computation of multiple input batches. As shown in this figure, we can put 3 layers on 3 devices. And then we can keep all the devices busy by letting them work on different input batches. So the intra-operator and intra-operator parallelism can also be combined, as shown in this figure on the right. So we first cut the graph in the middle into 2 parts for intra-operator parallelism. And then for each subgraph, we do intra-operator parallelism inside each subgraph. So for a mixture of expert model developed by Google, we can get the best performance only when we combine these 2 parallelisms, as shown in this figure. So in summary, all these choices form a very, very complex space with many trade-offs. And given a model of interest, it's very hard to efficiently search for a good strategy in this entire space. So however, this is still not the most tricky part. So the next tricky part is how to map the partitioning to actual devices. So after partitioning the graph, we have to map the partitioning to devices. So here is 1 GPU. It is definitely not enough for training large models, right? So I get a machine with 4 GPUs and more machines with more GPUs. So here comes the tricky part. So the network used to connect these machines shows a 2-level hierarchy, where we have fast connections for GPUs inside the node, such as the NVLink technology, and slower connections across different nodes, such as like InfiniBand or Ethernet. And the challenge here is how to map the graph partitioning to this 2-level hierarchy, right? So as you can see, the problem is challenging and very important. And in the past few years, people have developed various systems to solve this problem in order to train larger model. And I will list a few here. Each of the projects here below is developed by a good team of researchers and engineers. And each technique also typically enables a breakthrough on the machine learning side. So to classify them, I drew 3 circles. So red circle for intra-operator parallelism, and the yellow circle for intra-operator parallelism, and the blue circle for whether the technique can be applied to an arbitrary model automatically. So first, people design specialized strategies for specific models. NVIDIA's Megatron LLM system is a good example. It designs a specific model parallel strategy for parallelizing the transformer language model like GPT-3. And later, they improve it by adding intra-operator parallelism for better scalability. And there are also a lot of other systems trying to address this problem. However, they either cannot support both types of parallelisms, or cannot automatically apply it to a customized model. And in contrast, Alpa is the first system that can solve both types of parallelisms automatically. And next, I will spend a few minutes to tell you more about Alpa. So in the Alpa project, our goal is to build an unified compiler that can automatically find and execute the best strategy with both inter- and intra-operator parallelism for large deep learning models. So Alpa has a very simple API. So Alpa provides a Python declarator at alpa.parallelize. And you can put this declarator on top of your Python function, deep learning training function. And when this function is being called for the first time, it triggers compilation. And then the function will be parallelized and run distributedly on your cluster. So under the hood, this simple API is made possible by several innovations of this Alpa project. To deal with the complicated search space of model parallelism techniques, we organize them as a two-level hierarchical space. We then design optimization algorithms to derive effective parallelization plans at each level. And finally, we implement an efficient compiler to generate the plan and a very high-performance runtime to execute the plan on top of array. So given an input computational graph shown on this slide, the entire model parallel strategy space is a combination of all inter- and intra-operator parallelism strategy. But we want to find the best performed one from this big and complex space. And existing systems fail to do this because they do this either by human experts or they do this for one specific model like GPT-3. So in Alpa, the key to make this problem solvable is to decouple and reorganize this search space. So more specifically, we first search for the inter-operator parallel plan at the first level. And then at the next level, we derive the best intra-operator plan conditional on the inter-parallel plan. So we design the Alpa compiler based on this search space decomposition. And the input of the compiler is a computational graph and a cluster specification. And we design 3 compilation passes to do this optimization. So the inter-operator path finds the best inter-operator parallelism strategy with the dynamic programming algorithm. And the intra-operator path finds the best intra-operator parallel strategy with an integer linear programming algorithm. And this optimization is also hierarchical, which means that the higher level inter-operator path will call the lower level intra-operator path multiple times and make decisions based on the feedback from the second path. And finally, the runtime orchestration path will realize this parallel plan and actually execute the strategy on a array cluster. So let me walk you through an example and show what each path does. So for the inter-operator path with the given computational graph, we need to partition the graph into multiple subgraphs, which we call stages to form a pipeline. And there are different ways to partition the graph, and we need to select the best one of them. And here, assume our algorithm picked the first one as the best one. So which partition the graph into 4 stages here, shown in 4 different colors. We still need to assign each pipeline stage to a set of devices to execute the stage, as this slide shows. So in Alpa, we abstract all the computational devices, such as GPUs in a array cluster, as a 2D device mesh. And we assume that the devices along each mesh dimension has the same communication property. So for example, for a typical GPU cluster, we can set the one dimension to be all the nodes. And all the communication along this dimension will go through slower cross-node Ethernet. And we can set another dimension to be all the GPUs inside a node. And here, the communication will go through faster connections, like NVLink. So then we assign each stage to a subset of devices from the entire cluster by picking the best subset of devices for each stage. We call each subset of device a submesh of the original cluster. So following these procedures, here we have 2 problems. First, how to partition the computational graph into multiple stages, right? And second, how to assign the partition stages to submeshes from the cluster. And in Alpa, we find the joint of these 2 problems can be nicely formulated as a dynamic programming algorithm to minimize the total pipeline execution latency. And more details about this algorithm can be found in our project page. And with this inter-op path, we obtain a lot of stage and submesh pairs after partitioning and mapping. And let's now focus on the intra-operator path. So for a single stage and a submesh of devices from the inter-operator path, the goal here is to parallelize the stage on the devices in the submesh using the best intra-operator parallel strategy possible. And in Alpa, we find that this problem can be formulated as an integer linear programming problem. So specifically, the choices of different parallel strategies for each operator in the computational graph can be formulated as a decision vector in the LP. And the optimal parallel strategy should minimize this LP objective, which is the sum of the computational cost of each parallelized operator and the communication cost between different parallelized operators. Again, more details can be found in our project documentation. So with this intra and intra-operator paths, we can transform the original single-node computational graph to this parallelized pipeline stages. And with no existing framework supporting executing such a complex parallel plan, we also design a runtime to efficiently execute this parallel plan. So specifically, we compile each stage to an executable with static instructions. And this executable are then sent to the corresponding sub-meshes. And the Alpa runtime orchestrates intra-operator parallelism within a mesh, and the intra-operator parallelism across multiple device meshes. And we also implement the various optimizations for cross-mesh communication in the runtime with more details in our code base. So we implement Alpa as a compiler stack, and this slides give you an overview of the architecture of how Alpa is implemented and how it is built on top of Ray. So given the code of the model, we extract its computation as a computational graph in the format of a JAX-PR and intermediate representation used in the framework JAX. And the inter-op pass is performed on this JAX-PR to slice the graph into stages. And each stage is then lowered to another intermediate representation called HLO, developed by Google SLA compiler. And we perform the intra-op LP pass on the lower level HLO representation. And finally, Alpa compiles these representations into executables and sends them to device meshes and workers, which are implemented using Ray and as a lot of Ray actors. That's a brief introduction about the technology behind Alpa, and more details can be found in our paper and our project page. Now, let's move on to talk about the use cases the current Alpa project offers. So in the current Alpa project, we offer 3 main use cases that are readily available: train, serve, and fine-tune, but all for big models that existing systems or solutions cannot handle well due to the difficult problems I mentioned at the start of this presentation. So on training, Alpa can train models, large models like GPT-3 with state-of-the-art performance. On serving, Alpa can serve existing pre-trained large models like Meta's OPT with 175 billion parameters with minimized cost. And on fine-tuning, Alpa provides a lot of flexibility, which means that by using Alpa, you might have more space to customize your model architecture, and Alpa will generate flexible parallel strategies for your specific model architecture and cluster. So we started developing Alpa from training large models. So Alpa's single declarator interface is made very simple, and the backend is highly optimized on several typical training workloads of big models, such as training big transformer models like GPT-3, or training big mixture of expert models like Google's G-Shard MOE, or big computer vision models such as WebResNet. And all you need to do is to first start Ray, and then append this single line on top of your train step function, and Alpa will trigger the compilation and distribute the training workload on the Ray cluster automatically with high performance. So in training, people care a lot about the training performance. So let's talk about training performance. We compare Alpa with previous works on 3 widely used models. So for GPT, the standard transformer model, we test for models up to 39 billion parameters. And the transformer is an extensively studied model, and we can match the performance of the best existing expert design framework. Actually, we find that almost identical parallel strategy as the best manual system. And for G-Shard MOE is a transformer with additional mixture of expert layers, and we test for models up to 70 billion parameters. And we show that we can outperform the best manual baseline on GPUs by up to 8 times faster on AWS cluster. And for WebResNet, which is a significantly different model compared to transformers, and there's no existing manual model parallel strategy for it. And we show that we can generalize to this model without manual plans, while other systems would fail. So on serving, Alpa provides the first public, unlimited, and free text generation for the recently open-sourced large language model OPT with 175 billion parameters. And you can try it immediately now at this link, https://opt.alpa.ai. And here's a screenshot. So basically, you can type the prompts, and our serving cluster will use several GPUs to run inference for your requests. And we announced this service to a few university mailing lists about 2 weeks ago, and it went viral immediately on Twitter, and a lot of users have expressed their interest. And on serving, Alpa has 3 unique advantages. So first, Alpa serving is designed for serving large models like GPT-3, while most existing serving systems are limited to serve small models that must fit on one single GPU or TPU. And second, Alpa can use commodity hardware to serve the largest models. With Alpa, you can serve OPT 175 billion using your in-house GPU cluster, while many existing systems have a harder requirement on leading the latest generation of A100 GPU with 80 gig memory and high bandwidth like connections like InfiniBand, which are very expensive and hard to get. But Alpa helps eliminate this constraint. And third, since Alpa is a compiler, it also means that it's very flexible. It will generate the optimal parallel strategy depending on your available hardware and the model you want to serve. With these three advantages, put in other words, Alpa makes large models more accessible to everyone. And we provide a step-by-step tutorial on how to set up your own GPT-3-like service in the link below. And feel free to follow this tutorial if you want to do this in your cluster. And training a big model is very expensive, and it's estimated that training a big model costs several $1 million if you do it with the GPU's instance on a public cloud. This is not affordable for small companies or research groups. So fortunately, the community loves open science, and there are some groups that use the available resources they have to train big models, and then give open access of this pre-trained weights to everyone. So this page shows a few public available big models. So the first model, Bloom, was released by Big Science just 1 month ago. It is trained on 59 languages, and it's the largest public available language model currently. And Meta's OPT 175 billion is another large model released by Meta AI several months ago. And there's another model called GPT Neo X 20B. It's a smaller model released earlier this year. And the last feature we are actually developing in Alpa is to allow users to modify these existing pre-trained large models with customized components and support fine-tuning these models with flexible parallelism strategies. And Alpa actually supports fine-tuning all these models. And again, Alpa has a readily available tutorial and code examples on how to fine-tune these models. Please check it out. So with that, I want to wrap up my talk with a quick summary. So we presented the Alpa project for automatic model parallel training with both intra-operator and intra-operator parallelism. And Alpa matches or outperforms specialized systems and generalizes to new models. And Alpa provides use case for big models, and you can train, serve, or fine-tune big models on Alpa without worrying about how to parallelize their computation anymore. So you can try Alpa immediately using our unlimited generation service. Please do not hesitate to start Alpa project on GitHub to support our development. And thanks everyone for attending my talk, and I'm happy to take a few questions.
Hi, very interesting design choices here. So I have two questions. First is something I'm not able to wrap my head around. It's which all operators can be parallelized using this intra-operator parallelism? What characteristics or they need? And the second is, now that you have this big optimization problem, are you able to guarantee like load balance across these different GPUs that you use to serve?
Yeah. So the first problem is which kind of operator in machine learning programs need to be parallelized, right? Yeah. So typically, I think a lot of like matrix multiplication operators need to be parallelized. But like matrix multiplication can appear in many different forms, such as 2D, 3D, 4D, or conv2D, conv3D, or conv1D. And all these operators, when their input are very large, that cannot fit on a single GPU, you have to consider how to parallelize them. And this happens for models like GPT-3. Basically, each matrix multiplication, like those in attentions, like those in MLPs, need to be parallelized because they cannot be fit into one single GPU. So your second question is, can we guarantee load balance or say optimality when we perform this kind of compilation pass? The short answer is we cannot, but we are the best compared to other systems, which we can provide limited guarantee, but others cannot provide any guarantee. Yeah, cool. Because this problem is so difficult that I don't think it's hard. you can guarantee optimality. Yeah, cool. Yeah.
Hi, it was a really good talk, but I have two questions as well. First one is, why do you have to do ILP versus something like SMT solving for the optimization problem?
I think both are doable because we choose ILP because IOP is a pretty well-developed community, and you can find a lot of free servers which can run efficiently. Yeah.
Okay.
Yeah.
And the second one is for the cost estimation. Are you doing it using like a heuristic, or are you doing it using empirical measurements?
We are using a combined method. So the method has two components. The first component is a cost model. For example, alpha beta model, where, for example, the communication time is alpha, which is the latency plus the size of message divided by beta, which is the communication bandwidth. But this model cannot always run accurately. So we also have a second component which will run profiling before actually you perform this optimization. That profiling will run that model, give a strategy on the cluster for a few iterations and get some real estimation. And then combine this together, we can get a very good enough cost model. Yeah.
For that first part, are you using a arithmetic intensity?
Yeah.
Okay.
Yeah,
estimate.
like that.
Okay.
Yeah. Cool.
Hi. Thanks for the talk. So one question on the serving part, I wonder if the model partitioning that you are doing can do actually for any arbitrary checkpoints, or this is like specific to this model and you are partitioning it based on the known architecture of OPT or?
That's a really good question. So without Alpa, if you use any other existing systems, the way that they handle this partitioning is they will ask a team of experts to design a specific partitioning for that specific model. But the difference of Alpa is a compiler. It will look at the model architecture and run a few optimizations and automatically figure it out. So basically, whatever your model input is, like model definition is, Alpa will run optimization and get that best strategy, partitioning strategy.
And the second part of the question is about how you are actually optimizing the batch inferencing, kind of how you are optimizing about that. Because
I think you are asking something about how to increase the throughput of this serving system, right?
Basically, when you are sharding your model among different GPUs, and so it seems that you have to have kind of pipelining to kind of utilize all the GPUs.
Yes.
So how are you handling it for the serving part?
For serving, I think the pipeline is much easier than training, because in serving you can think that as infinite streaming. And what you need to do is just pipelining the incoming request following the pipeline parallelism. And you don't have to address some hard questions such as a backward propagation dependency, which is much easier. So basically what we do is we just apply our algorithm for training, but we eliminate that hard part, which is the back propagation part, and that will naturally works. Yeah.
I see.
Yeah.
Thank you.
Cool.
Hi. So thanks for the wonderful talk. So I have several questions. So the first one is for the integer programming program. Are you sure you got the optimal solutions, or it's like a suboptimal solutions?
In our problem formulation is optimal, but like I said, we reduce the problem a lot. So I cannot guarantee that it's optimal in its original problem setting. Yeah.
Okay. Yeah. Or one of my thoughts is, did you try using the RLab to formulating a reinforcement problem and to solve how to deploy the mesh?
Good question. So we considered that, but on one hand, I feel reinforcement learning is not so efficient, especially when your model is so big that have so many operators. On the other hand, I don't think in practice people like that, because they like optimality. They want like a deterministic answer so they can debug the system. If you apply reinforcement learning, okay, every time your strategy is different, returned by that server with a different strategy, and people can feel hard to debug their program. They probably would not like to use your system anymore. Yeah, that's my personal opinion. Yeah.
So thank you. So last is a quite open question. So how do you see Alpa compare with Google's pathway?
That's a really good question. We are almost a three-person team, and Google has a big team. But for now, I think Alpa has a few advantages. First, Alpa supports GPU pretty well, and I don't think Google care about GPU. They mainly focus on TPU, right? Second is, I think we are trying to build on top of the Ray ecosystem, and Ray already has a lot of users, and the people who like to use Ray will also feel Alpa a smooth experience, because what you need to do is just decorate your code and start Ray cluster. In terms of optimization, I feel at least theoretical wise, I think Alpa can provide more optimality guarantee compared to Pathway, because Pathway does not actually perform this kind of automatic optimization for parallel strategies. And Alpa does have some optimality guarantee and like theory. Yeah. Cool.
have a quick question about kind of roadmap and possible future integrations. Google has this plan to kind of split XLA into its own repo, OpenXLA.
Yeah.
Do you think Alpa could become just a powerful set of XLA passes? Or
Yeah, that's what is happening. So we have a contributor who is actually inside the XLA team. And one of our optimization paths, that LP path, is being ported into XLA. And I think you will see it soon in the public XLA repo. Yeah.
Okay,
yeah.
cool.
Yeah.
So eventually all of the Alpa technology could just be a set of XLA passes? That's a possible future?
I don't think so, because only the LP part will be, the intra-op part will be XLA, because the XLA team and Google only cares about TPU, and TPU has very fast connections. There's no slow connections. And in that setting, I don't think people would prefer pipeline parallelism or intra-operator parallelism. But in our, outside of Google, I think people are still relying on a lot of GPU clusters, right? Not TPU clusters, and people care about this intra-operator parallelism. And that part is what Alpa offers for this sort of GPU clusters. Yeah, cool. Yeah, I think we are at the end, and I'm happy to take more questions offline. Yeah, thank you.